Welcome back to The Explainer. Today we're doing something a little different. We are looking beneath the glass and metal of literally every device you own to explore the absolute bedrock of modern computing. We're talking about the operating system. It's the ultimate load-bearing foundation that bridges your physical hardware and, well, everything you actually do on a screen.
Really think about it for a second. How exactly does your smartphone balance 1,000 tasks at once? I mean, you're streaming a video, downloading files, getting pinged with messages, staying secure, all without the whole thing just completely collapsing. It's a massive engineering puzzle. And the secret? It lies entirely in how the system's architecture is built from the ground up.
Okay, let's dive right in. Here's our roadmap for today. We'll start with the core of computing, move through early operating system designs, and see how engineers started adding layers and organization. Then, we'll hit the microkernel revolution, arrive at the modern modular approach, and finally, wrap up with why OS architecture matters.
First up, Section 1, the core of computing, the blueprint of your device. So, to truly grasp how our devices function, we really have to look at their master plan. Operating system structure is basically the internal organization that defines how all the different components communicate with each other. It's a delicate balancing act between performance, reliability, and maintenance. Honestly, it's a lot like city planning for your device. It dictates exactly how software behaves, where your data lives, and how all that digital traffic flows without causing a massive pileup.
Right, so what exactly makes up this digital city? Well, we've got process management, doling out CPU time, memory management to stop your apps from tripping all over each other, and of course the file system to keep your data organized. Add in device management, to actually talk to your keyboard or printer, and the user interface for us humans. The crazy part is, every single architecture we're looking at today has to wrangle all these moving parts at the exact same time.
Moving on to Section 2, Early Operating System Designs, where it was really all about speed over safety.
Going way back to the beginning, the earliest blueprint was the simple structure. You might know this one from classic systems like MS-DOS. Now, the trade-off here was pretty extreme. On one hand, execution was incredibly fast, mostly because the OS was talking directly to the hardware. But the massive downside? It's like everything was thrown into one totally chaotic room. Because the components were so tightly connected, it was an absolute nightmare to try and debug or maintain.
To fix all that chaos, engineers came up with the monolithic structure, which you'd find in traditional Unix systems. Basically, they packed every single service, memory, files, drivers, the whole shebang, into one giant program running inside what's called kernel space. That's essentially the system's core brain. Now, performance stayed super high, but it introduced extreme fragility. Since everything shared that exact same space, a single error in one tiny module could literally crash the entire OS. I mean, one bad driver and the whole city burns down. Which brings us to Section 3, adding layers and organization, basically building for stability.
Okay, so constant system crashes were obviously a no-go, right? So the next big solution was the layered structure. This model takes the OS and divides it into very strict tiers. The lowest layer touches the hardware, and the highest layer serves the user. This was a real game changer for modularity. If something breaks in say, layer 3, you know exactly where to look. But yeah, there was a catch. Communication now had to pass through multiple layers. So while it definitely stopped the total crashes, it created this massive traffic jam that ended up slowing down overall performance.
All right, Section 4, the microkernel revolution. This is all about isolating the critical pieces.
Now, this concept was a massive paradigm shift. Instead of dealing with a bloated core, the microkernel structure took the kernel and stripped it down to just the absolute bare essentials, like basic scheduling. Everything else was pushed outward into user space, which is just an isolated area for applications. The sheer brilliance of this approach is fault isolation. Think about it. If a driver fails out in user space, it doesn't take down the core system. The only trade-off is a slight performance lag because messages are bouncing back and forth between those two spaces.
And you have to think about the real-world stakes here. Take the QNX microkernel, for example. It relies on this exact structure, and it's actually the brains inside automobiles, medical devices, and heavy industrial controls. When you're cruising at highway speeds or relying on a hospital heart monitor, you absolutely need that fault isolation. You just can't afford a total system crash because of some minor interface glitch. In these scenarios, the architecture is literally saving lives.
Moving into the modern era, Section 5, the modern modular approach, or as I like to call it, the Goldilocks solution.
So after literally decades of trial and error, engineers finally struck the perfect balance. We went all the way from the fast but super messy MS-DOS in the early 80s to the powerful but fragile Unix, then to those layered traffic jams, and finally to the super safe microkernel. By building on all those hard-learned lessons, we arrived at the modern era with the modular structure. And this is the very blueprint powering the billions of Linux and Android devices that we use every single day.
What makes the modular structure so incredibly exciting is how it combines the blazing performance of those old monolithic designs with the safety of a microkernel. Basically, the OS is made of independent modules that can be dynamically loaded right into the core system exactly when they're needed. This means a developer can upgrade a graphics driver or swap out a security protocol entirely on the fly. No need to modify, recompile, or, thankfully, crash the entire operating system.
Finally, Section 6, why OS architecture matters and the real-world impact of all this.
Looking back at all these engineering blueprints, the everyday value becomes incredibly clear. For the longest time, we constantly had to trade performance for reliability, or vice versa, right? Simple was fast but broke easily. Layered was stable but dragged. But by dynamically loading components, the modern modular structure finally solved the puzzle. It managed to hit the absolute holy grail: high performance, high reliability, and high maintainability, all at once.
Ultimately, a well-designed blueprint really is the secret sauce of all modern computing. By keeping functions separate, it guarantees system stability and really tightens up security around critical services. Plus, it makes life vastly easier for developers who are constantly pushing out updates. But crucially, it ensures that these systems can efficiently scale up as our hardware technology continues its rapid leap forward.
And honestly, seeing that evolution leaves us with a pretty fascinating question. As hardware just continues to advance, we've got quantum computing and dedicated AI chips entering the mainstream now, how will the operating system blueprints of tomorrow scale to meet entirely new demands? The modular approach is absolutely our gold standard right now, but as we know, technology never stands still. Thanks so much for exploring the bedrock of computing with me today. Keep asking those big questions, and I'll catch you in the next explainer.